We're gonna begin the advanced RNG settings lecture. I do apologize. This is gonna be kind of like theory heavy, because it kind of use some math to decide to make RNG to make better decision basically. And so yeah, let's just jump in. So these are the frequently encountered challenges when you use RNG. And I'm gonna try to talk about what are some settings that you can use in RNG to deal with them. The first that usually people encounter is people complain around RNG runs too slow or RNG crashes due to auto memory error. The second part of the talk will be on people sometimes will find that, oh, RNG generate a model, but that model doesn't have the species or reactions that I expect based on my chemical knowledge, or the model predicts some very high radical concentration that just does not make sense physically. I'm going to talk about the first, okay. So every setting in today's talk, it's some setting that you can put in your input.py. Mostly in this block, I get this screenshot from a super minimal case. So everything I talk about today, most of the time you can just put a setting code here, and I'll talk about what you should write here to get RNG to resolve these problems. And also, like, this talk is gonna be inherently theory heavy, so hope you have your copies ready. Okay, first RNG speed and memory limitations. The RNG speed limitation, it kind of run in different zones. In the early run, when there are fewer species in the core, or if these species have a lot of resonance structure, the RNG speed is limited by how fast RNG can generate all possible reactions for all the species in the core. And while later in the run, when you have more species and reactions in the core, it's limited by how fast RNG can solve the ODE system. So, but the transition between this regime is kind of very highly system dependent. So you kind of have to kind of see your system and see which regime is running in. So for the first possible way to speed up is quite straightforward. You use multiprocessing. You try to give RNG more cores that you can use so that it will parallelize the part that it generates all possible reactions. And it's quite easy to do this. You just give it a flag -n with how many processes that you want RNG to use, and it should parallelize that part. And the second thing that you can do is you can use species constraints. So what species constraint is, you tell RNG what kind of species that you allow it to generate. So for example, if you already know your system does not consider any biradical reaction, you can put it and say that tell RNG to only consider species that only have one radical, so that it will skip the consideration on the biradical part. And the reason why you can do this is sometimes for some species, especially like nitrogen or some certain species that can have a lot of possible radical resonance structure, RNG can really spend a long time to generate all the possible ones. And I have encountered sometimes I start RNG run and it will take like, I don't know, 20 minutes trying to figure out all the possible combinations, just because some species have a ton of them. So like using this flag, you can limit that number. And another thing that you can do is the speed that RNG generate reactions, or all the possible combinations of reactions, kind of scale with this number of reaction sites to the power of number of species. It's scaled really badly. And so you can put this constraint to tell RNG only consider a species size, you only allow it to grow to this number of carbon atoms, this number of oxygen atom, this number of nitrogen atom, to try to limit a possible reaction site. But to use this option, it kind of require you to a priori knowledge about what could be important in your system. And if you use it wrong, you might suffer from mechanism truncation. And the second way to speed up the generation of possible reactions is to use filtering. So how filtering works? So first, let's look at a case without filtering. We have some species D, E, and F in the core, and without filtering, RMG will directly just generate all the possible reactions. And with filtering, what it first do is it will try to provide an overestimate flux ratio with a theoretically upper limit of the rates to consider if in the fastest case possible, would this reaction be able to exceed our flux criteria? Like if even the upper limit will not exceed this number, then we think that, oh, whatever number that RMG came out with will not be important enough. So RMG will only generate those reactions that the upper limit can exceed this number, and it will only generate those. And this theoretically upper limit of rates are derived from based on some theory, and I think for bimolecular, it considers unimolecular, bimolecular, and primolecular reactions differently. And also it considers different limit for like gas phase and liquid phase. You can read more about how this upper limit is calculated from the RMG documentation. So the way you use this is simply in your model setting block, you turn filter reactions to true. And this is quite helpful in terms of limit the number of reactions that RMG need to generate and consider. And another possible way, so the previous part, we talked about how to speed up the generation of possible reactions. And in the later on, you want to speed up the time it takes to simulate reactors. And one possible way to do that is to switch to use RMS-based reactor. The difference is that compared to use in like simple reactor that we already use in super minimal, you can try to switch to other kind of reactor that we use inherently in the code, we use RMS code. So it's they tend to run faster. At least in my system, I noticed some very large speed up when I switch from liquid reactor to constant temperature volume liquid reactor. So this is one thing that you can do. And next, we're going to talk about the RMG memory limiting factor. And one thing that I guess like I want to stress is that memory, or people can call it RAM, is not equal to the disk space or the storage size. So your computer could have a lot of disk space that you can store, I don't know, 500 gigs in it, but it doesn't mean that it has that much memory. The memory is usually, I don't know, 8 gigs or 16 or 32 if you have. And most of the time, the species and reactions in the edge take up a lot of the space because there are a lot of possible combination of species and reactions there. And if the memory consumptions gets too high and RMG run out of memories, sometimes it will just terminate or it crashes. And here's kind of like an idea of how many number of species in the core and how many memory that it can consume. So it's still pretty bad because it's kind of like a combination explosion. The more species you have in the core, the more combination of possible product it can all form. And one way that you limit the RAM usage is to use pruning. The pruning idea is basically removes unimportant edge species and reactions. And there are two ways to do it. The first is using the flux ratio, and we'll refer it to as flux pruning. Basically, try to remove species that are formed at a very low flux, and they assume that it's not important. And second is to use Gibbs free energy of formation, and assume that if the formation energy is too high, then it won't be important at all in our mechanism. and that will refer to as thermal pruning. So first talk about flux pruning. Let's look at the normal case without pruning. So usually in the normal case without pruning, there are two parameters that you set. The first is the parameter called tolerance to move to core that we learned in the first day. It's like a tolerance where you compare the flux of possible species to the flux in the core and see how much this species could be important based on that. And there's a second parameter called tolerance interrupt simulation. It's basically saying that when you're simulating a core mechanism, when you already find a species whose flux ratio exceed this tolerance to move to core, there's no point to continue the rest of the simulation. You can just interrupt it and then do the next iteration of RMG thing, start considering your new round of possible reactions and stuff, because you don't need any information later in this later time, since you already found that important species. But in order to use pruning, there are three relevant parameters that you need to know what they mean. The first is tolerance to keeping edge. The meaning is that if a flux of a species does not exceed this number, it will assume that it's not important. It will delete it from the edge. In this way, it will keep your edge in a more like smaller size, basically. But you could also suffer from mechanism truncation because you assume some low flux species are not important, but you lose that information if in the future they are important, you don't know that anymore. The second thing that you should parameter that are relevant is, let's look at the no pruning case. One thing that we need to keep in mind is if we do an incomplete simulation, and if we apply that tolerance here, it's dangerous because we don't know how these two species will, how high their flux ratio will be in the future time. So in order to use flux pruning, you should remove this tolerance interrupt simulation up to allow RMG to do the full-time simulation. And based on the full-time simulation, you make that decision informed. So you have to move that tolerances up, and a third parameter that's relevant is maximum edge species. So if flux pruning is running, and if it can simulate a whole time span, it will do two things. First, it will try to check how many edge species you have. If it's larger than maximum edge species, it removes species based on from the smallest flux first until they reach this number. And it will also check whether there are edge species that has flux ratio lower than this parameter and remove that. So here, let's see, if we move the tolerance interrupt in simulation go up higher, we will allow the simulator to step forward in time. So you can see the current time step can keep stepping forward. It will do the full simulation, and it will then apply the tolerance to keeping edge. And now we'll see all the species has low flux of all the simulation time span, so we remove it. So the key thing here is that if you want pruning to work, you need to make your interrupt simulation to be higher. So here are the recommended parameters. If you don't use pruning, you usually want to set its tolerance to interrupt in simulation to be the same as tolerance to move to core, so that you don't waste time doing those extra simulation after you already find an important species. But if you do use pruning, you should add these parameters as well. You want to set your tolerance keeping edge to be, usually we'll find 1/10 to this tolerance move to core is good enough. And for the maximum edge species, you should start with something large, like 100,000. It's really limited by the available memory that your system has. Okay. Now we're gonna look at a thermal print. Oh, sorry. This is an example of how flux printing is useful. This mechanism, I think these figures were generated by Mark Payne when he tried to generate the mechanism for phenyldodecaine pyrolysis. So this shows that if you turn on pruning, it really helps you manage the memory consumption that RNG takes on your system. And in his case, he found that after cutting out those unnecessary edge species, RNG was able to even converge to a better mechanism. Although I would have to stress that this is not necessarily true for all the systems. You have to be careful. For some systems that have initially a low flux species, which, however, after many steps, it can accelerate some other reactions. That can happen too. And we will later talk about what do you do in that case. And we're going to look at the thermal pruning. So thermal pruning, the basic idea is that you remove species with high gift-free energy of formation. You use this tolerance thermal keeps species in edge. Basically, it's compare the new edge species to the gift-free energy of formation of all the species in the core. And if it's the new edge species if its gift-free energy of formation is higher than, say, 50% of the species in the core, then you would put 0.5 here. And so if I put 0.5 here, it means that I tell RNG to remove a edge species if it has gift-free energy of formation higher than 50% of the species in the core. So that's kind of the corresponding there. So the smaller you set, the smaller tolerance that you set here, the tighter it is because you will remove species more easily. This can be useful for some cases. In my system, like I know that my system only care about allylic radicals, but sometimes RNG would try to include, say, like a radical on the double bond, and I know that it's not gonna be important. But when I don't use thermal pruning, RNG adds all those possible combinations of radicals. But after I turn it on, it will remove that. So it's useful in that case. It will also check this maximum edge species and then if the number of species is larger than the species, then this tolerance, it will remove species based on their gift-free energy information, starting from the highest. It evaluates the gift-free energy of all the species based on the temperature of your system. So, yeah. Huh?
How does it get the entropy?
RNG estimate using the groups method. Okay, so these are the recommended parameters. So for this one, the possible range, usually you can use 0.1 to 1. This basically corresponds to that to remove edge species with gift-free energy formation higher than 10% to 100% of core species. And again, this one is relevant to how many memory available in your system. And I'm a little running out of time, so I'm gonna try to speed up a little more.
It's like RNG.
Exactly. The second part of the problem that you can have is species selection and pathway pickup problems. So the major thing is that RNG, okay. So a lot of time RNG cannot find certain species. Most of the time is because you don't have good enough parameters. So most of the time you should try first improve the thermal by doing quantum calculations or do some literature search to improve those parameters before you think that, oh, it might be the algorithm is wrong. Because we found that most of the time, like 99% of the time, it's that parameter that causing the trouble. But pickup problem can occur even when you have perfect estimates. And it's because RMG's flux-based algorithm, it assumes that species having higher flux are important and lower flux are not important. But we find many cases where low fluxes species can be important. So when these problems happen, they are harder to resolve. So among these two complaints, there are actually different problems. For the generate model doesn't have the reaction or species that we expect, there are 3 different scenarios. And for the model that predict very high radical concentration, there are like 2 different scenarios. The catalyzed problem means is this. We have a model, we have species A goes to B, goes to D, goes to E to form this species E. But there could be a low flux pathway that going from B to C and then C to Q, but Q plus A have a very high flux to form E. This can happen quite easily. I think in like combustion chemistry, there are many things like this. This is very difficult for RMG to figure out because in order for RMG to find Q, it has to first recognize, oh, B go to C is important, but B go to C have very low flux. So it's challenging for RMG. The second problem RMG can have is if A can become B and B can become 2 kind of species, and the sequence that RMG puts C or D into the core matters for. So like this is, if RMG only just have A to B reactions, the flux from B to C and B to D are high. So once RMG put one of them in the core, it will make RMG think that the other species is not important anymore because now it has low flux because this B species just goes to, say RMG takes C to the core, then all the B in the core will go to C directly, and there's only this very, very small amount of B left that can go to D. So it's like kind of that problem where why it's called orphan radical problem. This problem happens very frequently for radicals. And the third kind of problem is chain branching problem. This is like a low temperature combustion feedback loop. Even though this whole feedback loop have very low flux, this is actually the main pathways to generate radicals for this kind of mechanism. In order to solve this kind of problem that I just presented, there's a 3 possible ways to solve it in RMG now. First is you can try to add multiple species for this problem. You can tell RMG to, oh, just add C and D at the same time. There's a quite ideal way to think here because sometimes they don't actually appear to be exactly at the same time. It can be that some fluxes will exceed the tolerance first, and the other species go in between, and then the other radical that will appear. So this, you can do this, but it won't exactly solve that problem all the time. But using this, you can kind of speed up some generation to get to the size that you want, but not necessarily the best mechanism. But the way you do this is you set a maximum number of objects per iteration that RMG can put to core. Usually it's 1 to 2, 5, some number like that. And you can have RMG to terminate the simulation once it have the maximum number of objects so that you can save the time to simulate the rest of the reactor. But you should not turn this on if you're using pruning because you want it to finish whole simulation to prune species. So as you can see, the settings are kind of like intertwined that way. You have to kind of be clear what settings you want to use and think about how they interact with each other. And the second mechanism that can solve this kind of problem I just presented is to use the branching algorithm. Basically, it considers for a species a radical in a core. It computes 2 numbers. The first is the branching ratio. It's defined as a edge species. The flux of consumption by an edge reaction over the flux of consumption over of the all the core reactions for that one radical. And it defined as kind of like residual ratio, where you calculate the production of the core radicals minus the consumption of the core radicals. And you take the ratio with the characteristic flux in the core. And it kind of take this formula. So basically you're considering two things. How important this edge species contributes to the consumption of this one core radical, and how important this core radical is. That's kind of the physical meaning of these two numbers. And then you take those two numbers into calculate to decide whether this reaction in the edge is important. And you can use the branching parameters here. Matt Johnson found that the parameters are kind of like independent of the best parameters are kind of independent of the system. So this is the parameter that he recommends people to use. And he tested on the dodecane. I think Max tested this on dodecane paralysis. And the first one they don't use branching. The second one they use the branching algorithm. The third one they don't use branching algorithm, but they manually pick some products they already know is going to be important and add to RMG. And they found that the case with branching works really well. And the second thing that you can do in RMG to resolve this problem is, remember this slide from yesterday, to use transitory edge analysis on RMG. This feature is only available if you use the RMS reactor, because we do need to use the transitory code in RMS. And the way it does is that it evaluates the transitory sensitivity of the edge, for a species that you care about. So you can put a species here that you care about their sensitivity, and you put a tolerance here, and it will select the objects based on these tolerances. One thing to note is that transitory sensitivity can get quite expensive when your edge get very large, because you will construct a quite dense matrix. So you can specify to RMG to only perform this every 20 simulation time step to space it out and make it more affordable. And he tested this on Knox formation. Basically, the goal is for RMG to naturally find NO2. Using a normal setting, RMG were not quite able to find NO2, but if you use transitory sensitivity analysis, RMG eventually can find NO2. And one of the last thing is, if you suffer from this is a problem that I identified in my research. I found that the mechanism RMG generate have very high radical concentration, and we call it dead-end radical problem. And dead-end radical is when the radicals in the generating model by RMG are only consumed by very slow reverse reactions. This is the artifact errors that can be that caused by kind of like the inherent assumption that flux criteria make. The flux criteria assume low flux pathways are not important. So it has trouble to pick up some important chain transfer and termination reactions. This is a major problem, especially for molecular growth system, especially like polymerization and stuff, where you have a lot of monomers, and monomers directly form some major radicals. And for all the major radicals pathways, if they react with monomers or like major radicals recombine, these mostly have high enough fluxes that both branching algorithm and flux based algorithm can pick up. But there are a ton of radicals. So there are a ton of propagation reactions, which compete with a ton of chain transfer and termination reactions, which would have very low flux all by itself. But the combination of all these low flux reactions are important. So it's difficult because RMG thinks only a reaction is only important if itself has a high flux. it doesn't consider when all these combination of reactions have a high flux, it can cause a huge difference. So what this algorithm do is it considers this kind of a net consumption. It takes the difference between a consumption of a reaction and its production to make sure it's actually consuming radicals. And it calculates two things. One is the chain transfer flux ratio and termination flux ratio. Basically, compare the edge species consumption flux through chain transfer or termination, and compare it to the chain transfer consumption flux in the core. So like compare the same chemistry to same chemistry to make sure that we are doing a fair comparison. We're not comparing them to some very high flux propagation reactions and do that. And we're not gonna try to miss reactions because of that. Okay, the way you use this, basically you only need one parameter, tolerance reaction move to core, dead end radical. The physical meaning of it basically is that add this edge reaction to core if they contribute to more than 10% to 1% of core radical consumption and termination. I usually use 0.1. 0.1 works pretty well for my system. And I tested on butadiene polymerization. I use the same tolerance for fluxy. And in the first one is the most vanilla RMG flux algorithm. And the second one is I turn on the branching algorithm. The third one, I use the dead end radical tolerance. And as you can see, here are the percentage of radicals that are dead end, which are the radicals that are only consumed by very slow reactions. So when I turn on branching algorithm, it decreased that ratio a little bit. But when I use the dead end radical tolerance, it decreased it further more. It really changed the simulation result for the radical concentration. If you don't use it, you get a very high concentration of radicals in your system, and it can have like an order of 2 magnitude change in your system. It's quite large. And it can change the prediction of your model a lot. Okay, so this is quite a dense presentation. I try to put together everything that we have in RMG corresponding to different scenarios that you can encounter. Definitely check out RMG website. It has very detailed explanation on all of these that I just kind of give a summary about. And also definitely check out our recently released paper on ChemArchive. It really talks in details on a lot of the examples that I give. And thank you, everyone. Happy to take any questions.
So the transitory edge analysis is only RMS reactors. Is the branching ratio for all reactors?
Branching ratios for all reactors. Yeah.
The different algorithms, you able to use several at once, right? You can
Yes.
use the flux algorithm and the branching ratio.
Yes.
Okay.
Yes. I usually use a combination for my system. I use the default RMG flux. The default, you should always be using default RMG flux. And I use branching. I also add a dead end radical, and I turn on pruning for thermal and fluxes as well. I also allow RMG to add 2 object at once. I kind of like use the combination of all this. I just presented.
The thermo pruning is that throw away stuff from the edge if it's greater than 10% of stuff that's already in the core. Which means like if we know that all of this stuff in the core is important, I think like half of the stuff on the edge of it seemed I was surprised that you could throw away so much. I thought you'd have to like only if it's bigger than everything in the core do you throw it away.
Yeah, so theoretically, if you start from an empty core for RNG to generate everything, you should make that value large.
Okay.
But
That's
if
good.
you're starting with seed mechanism, then when you start with seed mechanism, you can use a smaller value because you assume all the important core reactions that you kind of have it already. So that's kind of like the catch of the thermal printing. You have to know your system quite well.
We should document them.
Yeah,
Yeah, it's a dangerous one, I think.
it is a dangerous one, yeah.
I know at least in the past, the pressure dependence didn't play nicely with some of these. Do you know which of these work with pressure dependence on?
I'm not sure. I haven't worked with pressure dependent system. I always, in my experience, I only work with liquid systems, so I don't really consider pressure dependent.
So anyway, just a warning, I think it would be good for us to get pressure dependence working with these. I think it probably works with some of them, but I think you probably need to do some extra. It was really working well enough.
I remember it took us ages to get it to work with pruning.
Yeah,
If you prune something from in a network, wasn't it?
we had a lot of trouble with that anyway. I don't know the status.
And if anyone wants to help me make RMG more memory efficient, so I don't have to worry about it. Even.
Real quick, the parallelization, like the Python -n,
Mhm.
what is that parallelizing, or is that just saying you're doing separate like runs of RMG?
No, it's doing the step that generate all possible reactions in
Oh,
parallel.
okay.
So, it consider, let me just move to the part, sorry. So there's the step, if I remember this, there's a step that RMG try to react all the the species, one species to apply unimolecular reactions, two species try to apply bimolecular reaction template. That's the step that they do the parallelization.
Okay.
And the key concept that they do this is because it kind of assumes that the isomorphism takes that all the time. So you try to parallelize that step. But yeah, but the parameter estimation part is still sequential, which is kind of inherent limitation that we use global database.
Yeah, one more comment about this is that this parallelization does actually give quite good speed ups in many cases. So it is parallelizing what's the slowest step. It unfortunately, the way it's implemented, you need copies of all of RNG on every CPU that's doing the calculation. And so the memory usage of the parallelization is high. So if you're making a big model, eventually what will happen is you'll use all the memory on a computer chip. And at that point, what will happen is that you'll turn off some of the parallel workers. And so your speed will seem to slow down. Like initially you'll be running and generating stuff really fast. And then it'll slow down because it's gradually turning off the number of threads that are running parallel because of memory limitations. So if you run on a bigger computer, it'll run fast longer. This is another one maybe related to Jackson's comment that there's things about the way the memory is handled that definitely could be better than they are.
It's actually even worse than that. They don't just like turn them off. They will like pause one, and then the computer spends a lot of time switching in and out of which one actually gets to run. So it wastes a ton of time writing things to memory and then writing them off of memory and back and forth. So, but yeah, so exactly what Bill said. If you get to a point where it was running very fast and then all of a sudden it just goes back to the performance of like one processor, that's probably exactly what it's doing. That would be a time to rethink your approach.
And again, if someone is motivated, I think this whole area, the memory usage and how to do parallelizations is an area where it is definitely possible to do it much better than we have done now. So this is like the first try.
To the filtering. So without filtering, you just react everything with everything when you put it into the core,
Mhm.
and then you forget about it. You reacted A with B, you found all of the A and G reactions. But with filtering, you only consider the reactions of A with B if B is high enough concentration, something, right? Because but then later, so that's already A and B in the core. In my mind, they're reactive. We've dealt with them. But later on, the concentrations of those might change because you've added other stuff and the core chemistry is different. We then have to go back and reconsider them. Is that
No, we
taken
do,
care of?
so
Yeah.
it keeps track and says we have to reconsider them.
It said this hasn't been considered.
Yeah, so
it
it keeps
keeps
track of the
track.
pairs.
Right,
Which
okay.
pairs have been considered so
Yeah,
far,
okay.
and I think this works, but apparently it conflicts with some other things. So I've seen situations where it's not working, but in the situations where it is working, often it's a huge speed up.
Yeah.
And so I think this is another one where some careful analysis of what's happening and why it doesn't work in some situations would be worthwhile to figure out. Because when your model gets big, the number of pairs AB is really huge, right? You have like 1,000 molecules in core.
Yeah.
Then it's 1,000,000 AB pairs. And if you only need like 1% of them, that's like a factor of 100 speed up. If you don't have to think of all these other ones. But it needs a lot of bookkeeping and keep track of all the pairs and what's been done and stuff like that. And, I've definitely seen cases where it worked. But I didn't, I noticed a lot of people run with it turned off. Because they must be having some problem. I don't know.
Yeah, I think we are done with this session and I want to save time so people can take a break. So let's just take a break, 5 minutes break.